Yeah, if you don't have one, get one.
And I'm recording this period because I had to yell at a bunch of people during second period because they just would not stay off their phones. I'm sorry I'm so boring, but if you could just, not be on your phones when we're trying to do calculations, that would be super cool. So anyway, so yeah, if you don't have a calculator, get one, and you do need paper for various things. Only one row. There's more scientifics down here, though. You can use scientific calculators. They are all scientific. All right. Wow. All by yourself, the bar and Madison, they're all gone. Okay. All right, ladies and gentlemen, let's pick up where we left off last time. I'm going to close this. So let's pick up where we left off last time. Last time we were talking about how atoms have electrons that can absorb energy. Remember, Niels Bohr said all the electrons are in shells. That's why I put out the 3D printed atoms for you. That's why I'm spending the last few weeks printing these things. So he said we have electrons and they're in shells. So if an electron starts in shell 0, it can jump up when it contains a specific amount of energy. And what was the word we used to talk about how the energy is a very specific amount? Where's the Q? Quantized, yes, quantized. It is a quantum of energy. So for instance, if level 2 is, or level 1 is 4 units away, it can absorb 4 units and jump up. If we give it 3 units of energy, what happens? Stays. Nothing happens, okay? And if we give it 5 units of energy, it still only jumps up to level 1. So that's the idea of quantized. The amount of energy between levels is a very specific amount. It's quantized. And then we know that once the electron jumps up, it generally doesn't spend much time there. It wants to jump back down. Now it might go jump, 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 but when it stops absorbing energy, it's going to jump back down, and it's going to give off energy, and hopefully the same amount of energy it took in. And then we talked about how different wavelengths of light correspond to different gaps, where a big gap corresponds to a high energy photon, like a blue or a green photon, and a small gap corresponds to a low energy photon, a low gap, like a red light. Make sense? Remember we talked about that? Okay. And what else did we talk about? And then we're going to use these formulas. So today, the big thrust of today is using these formulas and calculating the energies, the wavelengths, and the frequencies of various photons. This is something we can do. Okay. Now, what is C? Speed of light, right. So C is the speed of light, lambda is the wavelength, and F is the frequency. And we're going to spend some time talking about this. And then there's this number, 6.6 times 10 to the negative 34. This is called Planck's constant. And Planck's constant is something we can use to determine how much energy a photon is carrying. Remember what a photon is? What's a photon? Exactly. It's a single particle of light corresponding to a single quantum of light. And remember, when we say quantum, we mean a single thing. When we say quanta, we mean multiple things. So a photon comes from a single quantum of light. All right. If you have any questions, put your hand up and wave it around. No? Okay. We good? Give me a thumbs up if you're ready to move on. Okay. Now, today we're going to use some math and we're going to find out some important information about photons. First question. How fast is an X-ray traveling of wavelength of 3.2 nanometers? And nano is 10 to the negative 9. So it goes centi, milli, micro, nano. Nano is 10 to the negative 9. So nanometers is the wavelength, C base 10 to the negative 9. How fast is a wavelength, or an X-ray of wavelength 3.2 nanometers traveling?
C.
Exactly, yeah. No math needed. It's moving at C. It's moving at the speed of light. Okay, so exactly right. It's moving at the speed of light. So we don't care if it's a really long wavelength radio wave. Radio waves go from about yay big to bigger than your house to bigger than a football field. So we don't care if it's a really long wavelength radio wave or an itty bitty, you can't even see it, X-ray or ultraviolet light. If it's an electromagnetic wave, it's moving at C. Does this make sense? You better believe that's going to be a test question. Okay? Give me a thumbs up if that makes sense to you. So, how fast are infrared light traveling? C. How fast is ultraviolet moving? C. Good. Okay. Now this one is not a trick question. This one will require math. What is the wavelength of a radio wave with a frequency of 2.3 times 10 to the 9th hertz? So what formula should we use to determine the wavelength, which is going to be lambda, of a radio wave with a frequency of 2.3 times 10 to the 9th hertz? Is there a formula that links lambda and wavelength together?
C equals lambda times.
Yeah, lambda and frequency? Yep. So we're going to use C equals lambda F. And everyone remembers what C is?
Speed of light.
Speed of light, and numerically it is
3.0 times.
3.0 times 10 to the 8th, and the unit is meters per second, and that's going to be really important. So now we're looking for lambda. Lambda is going to be meters, and we're given a frequency of 2.3 times 10 to the 9th hertz. What is lambda? This is going to require your calculator. And just to give you an idea, this is about in the neighborhood of the waves that come out of your cell phone. I'm also happy to announce that I started writing a lab yesterday that we're going to do tomorrow, and it's going to take this math is going to be required in the lab. I used to do this in a simulation, but the simulation doesn't work with our computers anymore. So I was like, that sucks. I have some other things to do. Learn some stuff. So we're like, okay, let's make fire. We're going to make fire. Yeah. Oh, you're waiting. Again, if you don't like using the times 10 to the something, I would recommend putting this in as 3E8 divided by 2.3 E9. So if you don't like using times 10 to the whatever, putting them in parentheses, use your exponent key. This would be 3E8 divided by 2.3 E9. Give an answer.
0.13 meters.
Yeah, everybody get that? Or something in the neighborhood? Yeah, 0.13 meters. So how big is this wave? It's 0.13 meters, 13 centimeters. That's about yay big, about 13 centimeters. So the wave that's coming out of your cell phone is about yay big. Cool. Okay. Now I want to talk about units. This is really important. But before I talk about units, if you can understand why it's 0.13, give me a thumbs up. Back row? Yeah. If you don't understand why it's 0.13, put your hand up and wave it around so I can walk you through it. All right, so the formula we're going to use that links wavelength and frequency is the product of those two is going to be the speed of light. C equals lambda F. The exercise gives us the frequency F at 2.3 times 10 to the 9th hertz. So now we need to solve for lambda. And we're going to solve for lambda by getting lambda by itself and dividing 2.3 to the negative 9th over here. So we just rub a little algebra on it, single variable algebra, and we get 3E8 divided by 2.3 E9, and that's going to be 0.13. Okay. Now, there's something I want to talk about units. Units are very, very useful. And unfortunately, you've probably been taught that units aren't that important, because math teachers like to teach without them. But they're really handy, and I'll show you why. The unit for speed of light, C equals lambda F, the unit for speed of light is meters per second. Just like miles per hour. You look at the speedometer, it says miles per hour. Okay. Wavelength has the unit of meters. Frequency has the unit of hertz, but hertz is just a named unit. A named unit is a unit that we just named for somebody, just to say, you're cool, we'll name something after you, or most likely they're dead. You were cool, we'll name something after you. But frequency is actually how many bumps, how many peaks you get per second. How many bumps do you get? It's how many things happen per second. Okay? Like, you can have a frequency of heartbeats. You're like, oh, my frequency of heartbeat is 1.2 per second. You know, or 0.2 per second. So that's your frequency. It's how many you get per second. So it has the units of 1 over seconds. Can you see how the units cancel out? So meters per second and meters and per seconds. Okay, so the units cancel out. Meters per second for speed, meters for wavelength, and per seconds for frequency. They cancel out. Why is that handy? Because if your setup is correct, the units will always cancel out. Anytime in math, in English, or math and science, when you have units, if you put them in, they have to cancel out. Whatever's on one side of the equation will equal whatever's on the other side. So if you're not sure if I got the number, did I get the numbers in the right place? Well, put the units in. If the units cancel out, you probably put them in the right place. If they don't cancel out, you go like, squared meters, that's weird, or 1 over second squared, that's strange, then you probably didn't get them in the right place. Does this idea make sense, what I'm talking about? Does this make sense to you? Give me a thumbs up if you're with me. Okay, units are very handy. Remember in stoichiometry, remember in the T-chart method, we had the moles and the grams and the units cancel out? If you set it up properly, the units will cancel out. In conversion, you get what you need. You get moles or grams. Okay, next. Go back the other way. What is the frequency of a 500 nanometer green laser light? I happen to have such a laser right here. So, what is the frequency of a 500 nanometer green laser light? I have a laser with a really bad lens. The lens is completely trash. So give this a try. Now you're finding frequency. 500 nanometers is 500 times 10. 500 times 10 to the minus 9 meters, or 500 e negative 9. Okay, so we're going to use the same formula because now we're looking for frequency, which is f, and we're given wavelength. So wavelength is a distance. This wavelength of the light is 500 nanometers. It's really small. So we're going to use our same formula as before. We're going to use c equals lambda f. C is always going to be 3 times 10 to the 8 meters per second. Now, lambda is given to us, and we're solving for f. So lambda is going to be 500 times 10 to the negative 9, and now we're solving for f. Does that make sense? Question?
Where did you get the negative 9?
Because that's what nano is. Nano is negative 9. Kind of like milli is negative 3, and micro is negative 6, and centi is negative 2. Remember?
Yeah.
Nano is negative 9. this number be big, yo? You're dividing a very large number by a very, very small number. Yeah. Okay. You're dividing a very large number in 3 times 10 to the 8 by an itty bitty super tiny number of 500 times 10 to the negative 9. So you're going to get a huge number. Which makes sense, because when we're talking about frequency, what we're talking about is how many times the electrons go ba-boop as they leave the atom. Ba-boop, 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 ba-pew. So atoms move fast, so there's lots of ups and downs before they leave. How many ups and downs for green light?
6 times 10 to the 14th.
6 times 10 to the 14th hertz, which is 6 times 10 to the 14th every second. So it basically, this electron vibrates 6 times 10 to the 14th times every second, which is a lot. So if you could somehow slow down time with my green laser, what you'd see is a very small wavelength. You couldn't even see the wavelength. It's a wavelength. And then it goes up and down. The electrons bounce up and down 6 times 10 to the 14th times every second. And that creates the green light. Or at least creates the electromagnetic wave that you detect as green light. Okay. Does this make sense? Question?
Does that mean like solid objects like vibrate insanely fast?
The electrons do.
Yeah.
But solid objects, basically all the vibrations of the electrons kind of average out. There is something called the de Broglie wavelength where you can get solid objects to vibrate like electrons, but that's way beyond the scope of this course. If you want to learn about that, then take physics. Maybe we'll get to that going before. But yeah, so that is the vibration of electrons in the atom, causing they keep vibrating as they go.
Is it the more vibrations, the more visible it will be?
No, the more vibrations, the more energy they'll carry. So if it's a wave that falls into the visible range, which is usually in the neighborhood of 10 to the 14th, we'll be able to see that. But if it's a photon that has 10 to the 15th and the 16th, we're not going to be able to see that. Or if it's photons from 10 to the 13th, 10 to the 12th, we'll be able to see that either. So most things in the neighborhood of 10 to the 14th hertz, those are wavelengths. Those correspond to wavelengths that we can see. Good question. Okay, other questions? All right, I told you, and you wrote this down probably, that wavelength and frequency are inversely related. Because using this formula, if wavelength goes up, frequency has to go down. And if frequency goes up, wavelength has to go down. And using this equation, that E equals HF, we can say, based on the frequency, I know how much energy this photon is carrying. Planck's constant, that's how you spell it, P-L-A-N-K-S, Planck's constant. Planck's constant is basically a number that says, this is how much every bump in the frequency is carrying, how much energy it's carrying. Let me say it another way. The amount of vibrations an electron has, basically is analogous to how much energy it's carrying. And the variable that tells us exactly how much energy each photon has is Planck's constant. So now that we have a frequency, we can say, oh, now that I have the frequency, I can determine how much energy each photon of my green light is carrying.
So solve for energy on the last.
Yep, now you solve for energy. So you're using this formula, E equals HF. F is your frequency and H is your Planck's constant. So you can do some simple arithmetic and find out how much energy each of those photons is carrying. It's not very much, but that's okay. Yeah.
What does E stand for?
Energy. Yep, just energy.
Planck's constant.
Yeah, H is Planck's constant. 10 to the negative 4. Negative 34. Yeah, it's 6 times 6 times 10 to the negative, 6.6 times 10 to the negative 34. And the unit is joule seconds. We'll talk about it in a second. Once you've done the math, we'll talk about what joule seconds means. Why is there a calculator in the fidget bin?
Because you can play games.
The little screw that holds that together snapped. So individually it went. That was pretty much the coolest thing I've ever 3D printed. Because all 3D printed is one big piece. You print it and it worked. Didn't have to assemble. But the screw eventually snaps. Yeah. It's a little scissor jack. All right, if you got an answer, that number, can we round that number up to 4? If you got a number, if that makes sense to you, then you got the correct answer. What did you get?
3.96.
Times 10 to the negative
19.
10 to the negative 19 joules. So the answer is 4 times 10 to the negative 19 joules. Now, just like before, the units cancel out. Energy equals Planck's constant, h times frequency f. Energy is joules. Planck's constant is joules.